University of Toronto researcher Amanda Cook has found a way to use bright signals from universe to weigh the atmosphere of Milky Way galaxy. The signals it uses come from the astronomical phenomenon known as fast radio bursts, mysterious celestial bodies that produce short flashes of waves, and are considered one of the greatest mysteries in astronomy. Because an FRB simultaneously produces both high-frequency and low-frequency radio waves, different colors can be expected to reach a telescope simultaneously. An FRB slows down as it passes through the throttle more for high frequencies than for low frequencies. The result is a delay between different frequencies or colors reaching our telescope, effectively distorting the radio burst signal in time. Astronomers like Cook call this spotting scattering, and they can use it as a tool to detect gas that wouldn't normally be visible throughout the universe. Using a blot to study universe is in your home's heating bill to calculate what the weather should be like during winter, says Cook, a PhD candidate in astronomy and astrophysics by David A. Dunlap. Dunlap Institute of Astronomy and Astrophysics at the Faculty of Arts and Sciences. Just as your heating bill tells you whether winter was a harsh or a mild winter, but it doesn't tell you what temperature was like on any given date. Spotting we see allows us to understand total amount of material heat consumes. The FRB signal encountered on its journey from FRB to Earth. It cannot tell us how that material was distributed along the way. Importantly, no matter how gas in front of the disperses, an FRB signal that gets more smudged when it reaches our telescopes should be produced by a farther in same way as an expensive heating device. The bill must have meant a generally cold winter. An example of a radio signal from a fast radio burst traveling towards telescopes on Earth. In this case, Cook used scattering method to measure how much gas is present in the Milky Way halo, an atmosphere of Milky Way that extends outward for about 500,000 light-years in all directions. Using FRB signals collected by the Canadian Hydrogen Density Mapping Experiment radio telescope, Cook and his team discovered that the Milky Way halo contains far less gas than previous models had predicted. The results were a study titled, "An FRB Sent Me a DM," in the Astrophysical Journal. Although there have been previous studies applying related techniques, halo gas was first measured using a large uniform sample of FRBs thanks to the CHIME telescope. The team used FRB signals at different distances from Earth to get the result. Cook likens this approach calculating the average driving distance from different Canadian border crossings. Toronto, having friends from different American states go Toronto, only tell you the total distance they drove. The information you'll get from your Texan friend won't be particularly helpful, but your Michigan and New York friends' experience may be much more insightful. And if you have friends who live on the border, in Buffalo or Detroit, their answers will pretty much give you the information need. Cook and his advisor, Professor Bryan Gaensler, have been working on this research since he was a freshman graduate student. It's been a lot harder than we thought, Cook says. Hard enough, he, Gaensler, and their colleagues actually stepped outside of conventional astronomical models. They turned researchers in an entirely different field and asked these colleagues for a new set of methods to apply their approach. This is an exciting new way to study the Milky Way, says Gaensler, who is also one of the publication's authors. We're still trying to understand what fast radio bursts really are, but in the meantime, we can use them as projectors to study things much closer to our home. Cook and Gaensler note that FRB signals can be used to study the structure of everything the FRB signal passes through in its long journey, including material between galaxies, halos of other galaxies, and gas inside galaxies. Meanwhile, many more FRB discoveries are expected. With even more data, Cook and his team hope to create a 3D map of the Milky Way halo. Each FRB gives us a measurement of the Milky Way halo in one direction, so we can build a detailed picture as we continue to collect them, Cook says. Beyond that, he notes that these clues contribute to our understanding of the early universe. Improving our knowledge of the Milky Way halo helps us learn about the formation of our galaxy as a whole.